Pressure difference in a rotating fluid. Let us consider a tube of length L and a cross-sectional area A. Here is the tube of length L and cross-sectional area is A. The tube contains a liquid of density rho. Let the tube rotates about an axis as shown with angular speed omega. The tube rotates about an axis passing through its edge and perpendicular to its length with angular speed omega. We consider a small element of liquid of length dx at a distance x from the axis of rotation. From the axis of rotation at a distance x, we consider an element of length dx of the liquid. Mass of this element is dm equals to a rho dx. Since the area of cross section of the tube is a and length of this element is dx, its volume is a into dx and density of liquid is rho, so mass of this element is dm equals to a rho dx. This element rotates in a circle of radius x with angular speed omega. This element is at a distance x from the axis of rotation, so it rotates in a circle of radius x with angular speed omega. So centripetal force required for this element is dm into omega square x, since we know that centripetal force equals to m omega square r. For providing the centripetal force, pressure on right hand side of the element should be more than that on the left hand side. Pressure on right hand side of this element be little more than the pressure on left hand side of this element. Here we have taken that pressure on left hand side is P, whereas pressure on right hand side of this element is P plus dP. So force on right hand side of this element will be P plus dP into area of cross section, that is A. So we have P plus dP into A minus PA equals to dm into omega square x or a rho dx into omega square x. Actually, P plus dP into A minus PA is the net force acting towards the axis of rotation, which provides the required centripetal force dm omega square x or a rho dx omega square x. Therefore, we get dP equals to rho omega square x dx. So pressure difference between 2 points, one at the axis of rotation and other at a distance x from the axis of rotation. Here we can see that we have taken the element, its one end is situated on the axis of rotation and the other end is at a distance x from the axis of rotation. And we get delta P, that is difference in pressure between the two ends of this element of length x. Delta P equal to integration 0 to x rho omega square x dx, or delta P equals to half rho omega square x square. Here we have taken the 2 points, one at the axis of rotation and other is at a distance x from the axis of rotation. But if we want to calculate the pressure difference between the 2 points which are situated at a distance x1 and x2 from the axis of rotation, then we have to integrate this from x1 to x2. The pressure difference between 2 points at distances x1 and x2, where x2 is greater than x1 from the axis of rotation will be, here we can see that point x1 from the axis of rotation is here, and second point which is at a distance x2 from the axis of rotation is here, and pressure difference between these 2 points can be calculated as delta P integration x1 to x2 rho omega square x dx, or delta P equals to half rho omega square x2 square minus x1 square. So we can see the difference between the fluid in rest and fluid in rotational motion. When fluid is in rest, every point in the horizontal line has same pressure value. But when the liquid is rotating in a container, different point located at different distances from the axis of rotation has different value of pressure. A U-tube of length L contains a liquid. It is rotated with angular velocity omega about an axis which is coaxial to one of its vertical limbs as shown in figure. Calculate the difference in heights between the liquid columns in two vertical arms. Here we can see that the U-tube containing a liquid is rotating about an axis which goes through one of its limbs with an angular speed omega. The difference in liquid height between its two limbs is h. We have to calculate the value of h. Let the height of liquid in two vertical limbs are h1 and h2. So h equal to h2 minus h1. Consider 2 points 1 and 2 in the horizontal limb as shown. We take 2 points 1 and 2 in the same horizontal line in the horizontal limb as shown. Let pressure at these 2 points be P1 and P2. Due to rotation of the liquid, we get P2 equal to P1 plus half rho omega square L square. Here, rho is the density of the liquid. We know that as we move away from the axis of rotation, the pressure increases due to rotation by an amount half rho omega square L square, where L is the distance from the axis of rotation. So, the pressure at P2 should be greater than pressure at P1, and we get P2 equal to P1 plus half rho omega square L square. Again, P1 equals to P0 plus H1 rho g and P2 equals to P0 plus H2 rho g, where P0 is the atmospheric pressure. Since the two vertical limbs are open, so atmospheric pressure acts on the surface of this liquid, and we get P1 equals to P0 plus H1 rho g and P2 equals to P0 plus H2 rho g. From equation 1, if we put this value of P1 and P2, we get P0 plus H2 rho g equal to P0 plus H1 rho g plus half rho omega square L square, or P0 cancels from both sides, and we get H2 minus H1 rho g equals to half rho omega square L square, or H equal to omega square L square by 2g. Here is another problem which states a vertical U-tube having two liquids of densities rho and 2 rho is rotating with an angular speed omega about a vertical axis passing through its left limb such that the liquid columns in the limbs have heights h and 3h as shown in figure. Calculate omega. Here the two liquids has densities rho and 2 rho respectively, and the height of the liquid column in the right limb is 3h and in the left limb it is h, and in the horizontal limb we can see that the liquid of density rho is of length 4h and liquid of density 2 rho is of length 3h. We have to find omega, that is the angular speed. Let pressure at point 1, 2 and 3 be P1, P2 and P3, where point 2 is on the intersection of two liquid. We have taken 3 points in the horizontal limb of the U-tube, 1, 2 and 3, where point 2 is on the intersection of two liquid, and let the pressure be P1, P2 and P3 in these 3 points. Since the liquid is rotating, so pressure P3 is greater than pressure P2 and P2 is also greater than P1. We know as we move away from the axis of rotation, the liquid pressure increases due to rotation. So P3 greater than P2 greater than P1. P2 minus P1. that is difference in pressure between point 2 and point 1 equals to half rho omega square 4h whole square minus 0 square. Here, point P1 is situated on the axis of rotation and P2 is at a distance 4h from the axis of rotation. So we get P2 minus P1 equals to half rho omega square 4h square minus 0 square equal to 8 rho omega square h square. Again, P3 minus P2. Here we can see this point 3 is at a distance 7h from the axis of rotation, but point 2 is at a distance 4h from the axis of rotation. So we get P3 minus P2 equal to half into 2 rho, since the density of this liquid is 2 rho, into omega square 7h square minus 4h square, or P3 minus P2 equals to 33 rho omega square h square. Adding these two equations, we get P3 minus P1 equals to 41 rho omega square h square. But P3 equals to P0 plus 3h g into 2 rho, so on P0 plus 6h rho g. The two vertical limbs of the U-tubes are open to air, so atmospheric pressure P0 acts on both sides, and we get pressure at P3 is atmospheric pressure P0 plus pressure of this liquid column of height 3h. So P3 equals to P0 plus 3h g into 2 rho equals to P0 plus 6h rho g. And P1 equals to P0 plus h rho g. So we get from equation 3, that is equation P3 minus P1 equals to 41 rho omega square h square, 5h rho g equals to 41 rho omega square h square, or omega equals to root over 5g by 41h.